Hello, my name is David Archer, and I'm a professor of geophysical sciences at the University of Chicago. And this is a short course on the greenhouse effect and the carbon cycle and climate change. The temperature of a planet is a topic that our understanding of goes back almost 200 years to a French guy in Napoleon's army named Fourier, who figured out that it's light that's coming into the planet and leaving the planet that determines what the temperature of the planet will be. When you think about it, the planet is in space. It means it's not touching anything. A vacuum is a very good insulator, so it's kind of astonishing that energy can hop across the nothing from one astronomical body to another. But that's how it works. It turns out that any object that has a temperature warmer than absolute zero will be constantly shedding infrared, shedding light, shining light. So the sun does that, we can see that. The Earth does that as well, but it's infrared light that we can't see with our eyes. We can measure it. So the Earth is continually bathed in sunlight, bringing energy in, and it's shedding energy. And over time, the energy fluxes have to balance because energy is conserved. There's only as much energy going out as coming in. And so it's kind of like a kitchen sink. If you turn on a faucet into a sink in your kitchen, the water level in the sink may rise a little bit. And as it rises, there's more and more pressure pushing water down the drain. And so the water level in the sink finds the value at which the water going down the drain is equal to the water coming in from the faucet. When you first turn it on, it sort of rises toward that level. Or if you came in with a big bucket of water and dumped it in all at once, it'd be higher than that level, but then it would go back to that steady state level in time. And this is a good analogy to the way the energy on the planet works. The temperature of the planet is analogous to the water level in the sink, and the higher the temperature of the planet goes, the faster it's shedding energy back to space. And so the temperature finds the value at which the energy fluxes balance just all by itself. So there are ways to tweak the steady temperature of the ground, just as you could probably tweak your kitchen sink if you have the water running and make it go to a different water level. So you could turn up the faucet so that water is coming in faster, and that would mean the water level would find a new higher value because it would have to be deeper to push the water down the drain. Or you could mess with the drain a little bit. Maybe a little piece of food or something gets stuck on the drain and it gets a little slower. And so even if the faucet stayed the same, if you plug up the drain a little bit, the water level in the sink would rise. And that's also analogous to the energy balance of the planet. We can alter either the energy coming into the planet by making the planet more shiny, whiter. If you have more clouds, clouds are really good at reflecting energy back to space. Or ice also is, snow is very, very shiny and reflective. So if energy is just bouncing back to space and not being absorbed as heat, then it sort of doesn't enter into the energy budget of the planet. It's sort of as though, some of the water out of your faucet is splashing onto the kitchen floor or something and not going down the drain. And then analogously to plugging up the drain a little bit, that's how greenhouse gases work. They impede energy leaving the planet, and so they make the planet sort of have to heat up more in order to overcome that impediment. And so just like putting a little piece of carrot on the drain in the kitchen sink causes the water level to rise, putting greenhouse gases in the atmosphere causes the temperature of the Earth to rise. The piece of carrot doesn't bring the water with it, but the water is flowing through the sink all the time, and that's where it comes from to rise. And that's the way it is with the energy in the atmosphere that the greenhouse gases trap as it's passing through the system, and it leads to a higher temperature of the planet. So if the Earth was just a naked rock in space, it would be pretty easy to just do an experiment in the lab, see how much more energy a rock sheds when you warm it up 1 degree C or something like that, and calculate how much warming there should be from adding new greenhouse gases to the atmosphere. So one measure of how much warming the planet gets is the climate sensitivity, defined as degrees of warming you would get from doubling the amount of CO2 in the atmosphere. So if the Earth were just a naked rock and there was nothing else going on, you would get about 1 degree C of warming. But it turns out that on Earth, if you warm the atmosphere, there are changes that happen to the atmosphere. This is called a feedback. So the biggest thing is if you have warmer air, there can be more water vapor in the air. And water is also a greenhouse gas. So you warm the planet up by putting CO2 in the air, and that causes the atmosphere to warm and causes more water vapor in the air. And water vapor is itself a greenhouse gas, so that causes the Earth to warm even more. So now the temperature change you get from doubling CO2 in the atmosphere has just gone from 1 degree C for a naked rock to like 2 degrees C. It's twice as strong. Another feedback is that if you warm up the ground, ice and snow will melt. And ice and snow are very reflective, as we said. They tend to lose energy by reflection rather than absorbing it. So when you melt the ice and snow and sea ice on the ocean, you absorb more energy, and that also makes the planet warm up even more than it would if it was just a simple naked rock with nothing else going on. So maybe now from doubling CO2, we might get 2.5 degrees of warming. And then the big loose cannon in the system, where we're hung up and it's hard to nail things down, is clouds. Clouds scatter visible light by being, hard for light to go through, but they also act as a greenhouse. And so they could either warm or cool the planet. Clouds are controlled by all kinds of little processes. It's all based on things that are so small and detailed that they're impossible at present to put them into global climate models the way we would really like to do. So different climate models have different responses of the clouds. Some of them, the clouds don't do much, and in them, the climate sensitivity is maybe 2.5 degrees C for doubling CO2, like we said. But other models, the clouds act as another positive feedback. So you end up with a climate sensitivity that might be 4 or 5 degrees C for doubling CO2. So that uncertainty is a really hard thing to eliminate. But those are the basic ideas that go into figuring out how the greenhouse effect works.